Hello, everyone. This is lecture 5 of PTRE 475. I uploaded a new updated slide deck, but the changes I made were like minor typos. I fixed an issue with example problem number 1 in the answer. That was a little bit off that Michael noticed it. And thank you, Michael, for that. And then some other small grammatical errors, typos here and there. So nothing really crazy in the changes to have to let you know. But we were, there was also an issue last time. It wasn't my fault. It took the system like 4 hours to create the video of the class. And I was looking for it. You could see it in the cloud, but you couldn't see the version that I could download and then upload separately on Blackboard. That's why it took me so long. I don't know why it took them so long to last Thursday to do that. And then next Thursday, not this Thursday, but next week Thursday, I'm gonna be gone. I will be in Houston for a conference, so there won't be class next Thursday, but we'll try to cover up. Let's see, last time we went through quite a bit of material. We talked about how to estimate the magnitude of the overburden. SV, we discussed how you do that. It's basically a simple mathematical approximation, but it's a complicated process to get those values. For you guys, if they give you those values, it's easy. For the geologist who has to estimate those values, it's a little bit hard, more challenging. 2 ways to approximate it that I have shown, but ultimately, whatever way you use, you are basically solving this integral that I have here, which is approximated by this. And then the common mistake that students do is that they use, when they are using oil field units, they use G as a separate variable, 32.2, and that messes up the answer. And I said, please don't. And when I was teaching geomechanics, I had a homework that you had to do the same answer, the same question with SI units and with oil field units to see the difference. Now, rule of thumb approximation for the depths that we are talking about, for the depths that we care about as petroleum engineers, overburden the lithostatic stress gradient approximately 1 psi per foot, which translates to 23 MPa per kilometer, and that compares to 0.43 psi per foot for fresh water, which translates, which is 9.8 MPa per kilometer. So more than double the weight of the fresh water is the weight of the overburden. It can be 0.8, it can be 0.9, it can be 1.2, can be 1.1, 1.05, obviously. But yeah, I mean, around 1, that's what you expect it to be. And the hydrostatic pressure gradient is always 0.433. That's the weight of the fresh water. Now, I mentioned last time that be careful when you see the word hydrostatic. Sometimes it might be referring to fresh water. Sometimes it might be referring to any fluid. You need to understand the way the word is used in context of the sentence. I guess it's a very confusing thing, because when we say the hydrostatic weight of this fluid is such and such, it doesn't mean that this fluid is fresh water. But if we say things like, you can assume the pore pressure of this reservoir is hydrostatic, that means assume that you have fresh water all the way down to that depth. What would be the pressure? And that would be the pressure of the reservoir. So you need to be very careful. I say that to the students in advanced drilling as well. it can be very tricky because they use these words interchangeably. We talk about offshore, you need to account for the weight of the seawater above you. US Gulf, roughly 0.465. That's another way you can approximate that integral for the overburden if you want. It's the same as the one in the previous page. The only difference is that with this equation is if you have the depth of the layer at the middle of each layer, not at the beginning and the end, as we had in the previous slide. So to use this equation here, it's if I give you the values, sorry. If I give you the values, these values, and if I give you the depth sort of here, the depth here, the depth here, the depth here. So that's another way of approximating your answer. Then we talk about estimating the SH mean magnitude. Not always. I don't know if I stressed it enough last time, but I wanted to say that the Likov test is not going to give you the approximation, an approximate estimate of SH mean everywhere. It's true in strike slip faulting and normal faulting. It's not true in reverse faulting. There is a reason for that, and we'll understand it later. Well, you already know from geomechanics that in reverse faulting, the smallest stress, least compressive, is the overburden, SV. So if you do a Likov test in a reverse faulting stress state, you're not going to get SH mean. You're going to get SV estimation. That's the whole idea behind it. It will become clearer later on in later lectures, later in the semester. And we spent some time on this plot, and we will spend time on this kind of plots later on in this semester as we get more into hydraulic fracturing. It's just I want you to know that the lowest point at which a fracture can start is the leak-off point, where the fluid starts leaking into the surrounding formation that's here. And the biggest is going to be somewhere here. We call it the FBP, the formation breakdown pressure. After that, the pressure drops. And then if you keep pumping, it levels off. That's what you do in hydraulic fracturing. For leak-off test, you are going to end the test much earlier. Much earlier. So that's how you estimate SH mean. It's much more complicated than overburden. Several ways to do those tests, plural, several ways. And then when it comes to SH max, it's the hardest of all, okay? Regardless of where you are. I have seen papers written just for and master's projects being made just to find the SH max magnitude in a certain location, because it's so hard to estimate. It's between the most of the times SH max is well, normal faulting is between SV and SH mean, so it's very, very hard to constrain. Other times it's the most compressive, like in reverse faulting and in strike slip faulting. For vertical wells, this equation here is it can be used to approximate SH max. Now, this is not universally applicable. It's only in some places applicable. And we will understand how this equation, this approximation is being derived. We are going to see it later. We're going to get back to it eventually. Now, it says SH max is roughly equal to 3 times SH mean minus FIP minus PP, which is the pore pressure, plus T, which is the tensile strength of the rock that is often being neglected or, I guess, ignored. For reference, gypsum has, which is calcium sulfate, 294 psi, 300 psi. Hydrostone, which is cement close to rock, something like 700 psi. Now, if you have SH mean that is like 10,000 psi, like in the bucket, and sorry, SH mean in the bucket is like 8,000 psi. SH max is roughly 10,000 psi, a little bit over 10,000 psi. Say that the tensile strength is 1,000 psi. It's still not high enough. You can still sort of ignore it. You can certainly ignore it if it's 500 or like around there. I mean, I certainly don't think that the tensile strength of the bucket is 1,000. It's much less than that. It's something like less than 500, probably. So you can possibly ignore it, but it's not always the case. For our class, I will tell you if you have to ignore it or not. Now, FIP in this equation is, we said you can have fractures initiating from pressures as low as the leak-off pressure to as high as the formation breakdown pressure. Leak-off pressure is the lowest pressure at which you can get a fracture to initiate. That's pretty low. That's where you normally get fluid leaking into the surrounding formation. Formation breakdown pressure is the highest pressure the well will ever feel, most likely in its lifetime. So that's a very high value. So the gap is, the range is very, very low, very, very wide, WIDE. So when we say approximate SH max, it can give you a very high range here. It might not be good enough to give us like an answer that is within a short range that will make sense. In homework 1, which will come probably next month, or certainly next month, beginning part of next month, I believe, we'll see an example where you can use the observation of drilling-induced tensile fractures to constrain the SH max. We're going to see an example where this is done very effectively. And that is, you have, during drilling, you have some fractures that take place naturally. They are called drilling-induced tensile fractures. And they show up on image logs, which is like, image log is an image of the borehole. So you can see those DITFs. Those DITFs have the same DNA as the hydraulic fractures that you do during stimulation. They have the same DNA as the fractures you initiate when you have in drilling what we call underground blowout. They are the same thing. All of them are what we call tensile fractures. So the mathematics are the same for all of them. And there are some places, there was a place where the observation of those fractures, the ITFs from image logs, helped constrain the magnitude of SH max. And this is what you are going to do in your homework 1 when the time comes. It's not right now. You will see some stuff before we get there. Okay, now we start for today. We're going to get a little bit more theoretical, tiny bit more theoretical. And that is we're going to talk about fracture modes. And this is where we stopped last time. I told you, drilling-induced tensile fractures, hydraulic fractures, underground blowouts, same thing. And I said mode 1, sorry, tensile fractures. Now, tensile fractures, mechanically speaking, is what solid mechanics people call mode 1 or opening mode. So imagine this piece of metal or whatever it is, you're pulling it apart, you are rupturing. Pulling it apart is like take chopsticks from an Asian restaurant, Chinese restaurant, flip it upside down, pull them apart. That is open mode or mode 1 fractures. Then, and this is basically tensile breaking of the material is like you are working against the tensile strength of the material. The higher the tensile strength of the material, the higher the T, the harder it is to break the rock in that fashion. I said something 2 lectures ago that maybe 3, that we use a different convention from the solid mechanics people. They use compression positive, tension positive, compression negative. But for us in the Earth, we use compression positive, tension negative, because down the Earth you have much more compression than what you have tension. Now, that being said, in most of these applications in the subsurface that are outside of petroleum engineering, it's very rare that you're gonna see mode 1 fractures, okay? You need human intervention to create those mode 1 fractures because there is not a lot of tension naturally occurring in the Earth's subsurface. There is a lot of compression, but there is not a lot of tension, okay? When I was doing my postdoc in civil engineering, we only care about non-tensile failure, something called shear failure. We rarely talk about tension at all. And that's because you do not have humans trying to create this kind of failure. In petroleum engineering, you have humans trying to induce mode 1 fractures, for instance, during hydraulic fracturing. What you are trying to do is to make a lot of mode 1 fractures in the rock and basically create conduit for the fluid to move to your well. Now, that's mode 1. Let's see mode 2. Give you some examples here. Mode 2 is a sliding mode or in-plane shear fracturing. When you see shear, imagine like one piece of rock moving over each other in a certain direction. When they move on the same plane, it's in-plane shear. This is similar to the way that the rock breaks when you have earthquakes, okay? You make one piece of rock move over each other, like tectonic motion. It's one chunk of rock sliding next to each other, right? And you have shear. Now, you can have in-plane shear, it's mode 2. You have mode 3 is the tearing mode, it's out of plane shear. It's like a twisting mode, as they call it. And they call it opening mode, sliding mode for the second one, and then twisting or tearing mode. Imagine again, you have chopsticks from a restaurant, you twist them apart, that's mode 3. Out of plane shear. One example of that is when you have strike slip motion on the edges of those rocks, it's gonna be mode 3 failures. Now, let me say something that I don't expect you to know already, but I will give it to you as information. We said hydraulic fractures are mode 1, okay? Purely mode 1. The actual fracture is mode 1. But you'll hear a lot of people saying, oh, we did a microseismic study of during our hydraulic fracture job, and these are the results that we got. This is what we expect the fractures to look like in the subsurface that we cannot see. And the answer would be, I mean, you don't know it yet, but when we do microseismic, we detect mode 2 fractures. We don't detect mode 1. So if hydraulic fractures are mode 1, why do we use microseismic? And the answer is when you have no fracture is purely mode 1, no fracture is purely mode 2, no fracture is purely mode 3. When you open a hydraulic fracture, yes, on the crack tip, at the edge of the fracture, you have mode 1. But on the walls of the fracture, as it's moving, you have a lot of mode 2. And this is what is being detected by the microseismic. So that's why you can say I had microseismic and this is the results I received. This is how they look like. And I'm confident that my fracture looks like that. And somebody might say, oh, but this is mode 2. Mode 1 is aseismic. It doesn't give any seismic footprint. And they'll be like, okay, but you have a lot of mode 2 components in the walls of the fracture. I had an office mate back in the day when I was a student. He's now a professor at Oklahoma State University. He wrote a particle flow computation model for something that you may remember from geomechanics called semicircular bend test, which is you have some weird shaped sample that you put under stress and you create fractures. You cut it, you basically break it. The fracture that is created is one type in the crack tip, and you see a lot of you find footprints of all mode 1, mode 2, mode 3 as it goes along. Like you have all 3 basically. So it's very rare that you have a fracture that is purely only one of the 3 modes. Most of the time you have all 3. That's what I wanted to say. We are going to talk about the SCB testing in module 3. Okay, so now more complicated a little bit is we have a lot of we talk about stress states, okay? We said if SV is bigger than SH max and SH mean is normal faulting. If SH max is bigger than our reverse faulting, if SH max is bigger than SV, which is bigger than SH mean, is strike slip. If SH max is bigger than SH mean, which is bigger than SV, is reverse, and so on and so forth. That gives you an infinite amount of permutations for the stress state in the Earth subsurface. I can come up and ask somebody random, okay, give me a value of SV, and they say something. SH max, say something else. SH mean, say something else. Pore pressure gives me something else. So 10,000 psi, 800 psi, 6,000, sorry, 8,000 psi, 6,000 psi. And then somebody comes and says, 800 psi, 3,000 psi, 1,000 psi. Somebody comes and says, maybe 15,000 psi, 8,000 psi, 7,500 psi. I'm writing random numbers. I'm trying to tell you infinite permutations. Now, I want to ask you, Do you think that anything I can imagine and write down is possible to exist in the Earth subsurface? I don't think so. Then I will have an infinite amount of possible stress states. So I want to come up with a way to understand what is the range of stress states that I expect to see in the Earth subsurface. And this is what we're going to discuss in the next few slides. Are there any questions so far? Everything okay?
Yes, Professor. Yeah.
Okay, thank you, sir. So the logic I'm going to try to apply now is I'm going to say there are some stress states that if they do exist, they are going to lead to automatic failure. Okay, some kind of automatic failure. So those states, I would say they are unstable and they cannot exist. And I'll be like, okay, I don't expect to see this state because it's going to be unstable. It's possible hypothetically to exist, but in real life, that will cause me some sort of instability that will suggest that it's not stable. This is what I will try to do mathematically here. And the answer it has to do with fault slippage and those mode 2 fractures that we mentioned earlier. Let me see. Normal, reversed, or thrust and strike slip are terms not only used to characterize faults, but also used to characterize the local stress regime. I gave you an example last time. The Gulf is normal. East Coast is reverse. Several parts of the Midwest is strike slip. The West Coast is strike slip of the US, etc., etc. But not all stress state permutations would be stable in the Earth's subsurface. And the answer is that there are some stress states that if you have them, it will automatically trigger shear slippage along pre-existing faults. That means if I have a fault under those specific conditions, I will automatically have earthquake because the fault will move under those conditions. So I can say these hypothetical conditions cannot really exist because it would be an unstable situation. This is what I'm trying to say, basically, what I will try to discuss quantitatively. Now, when it comes to shear slippage, the situation is a little bit more complex to describe mathematically. It's not enough to use one stress. For tensile failure, if a stress becomes more tensile than the tensile strength of that material, you have tensile failure, end of story. For shear failure, you are comparing two stresses, the way the dynamic between them. You have the biggest stress, which is sigma 1, and you have the smallest stress, which is sigma 3. Okay? If you have a fault right in between them, in the material solid region that these stresses are acting upon, you have a fault. Those two stresses, sigma 1 and sigma 3, they will induce a shear stress on that fault and also a normal stress on that fault. Those two work against each other. The shear stress, tau, Greek letter tau, tau as they say in English, is trying to make the fault to slip. The sigma n, the normal stress, tries to keep the fault together. So if tau exceeds sigma n, satisfies the criterion that exceeds overpowers sigma n a certain way, you are gonna get full slippage. That is basically an earthquake. Doesn't mean earthquake like it might be fair. It means that it renders the stress state that between sigma 1 and sigma 3 being unstable. That means you're going to tell me, sir, I'm sorry, what you are trying to do in the lab doesn't make sense, because if you do have this stress state in the earth, it's going to lead to failure. So why are you doing this experiment under those stress states? It's impossible. That's basically what we're trying to do. And the way that those basically what you apply is sigma 1 and sigma 3. And then you have the pre-existing fault, and then you have you induce tau and you induce sigma n, and depending on those magnitudes, you see if you have slippage or not. That's the idea. Now, somebody may say, okay, what about these pre-existing faults? Do you have it everywhere? If you have it everywhere, is it like, it's not the same. It's not like every fault is the same. They all have different properties, different orientations, so on and so forth. And we're going to make some assumptions in those. Well, before that, I want to say here, we can say it here. Subject to the friction factor along the pre-existing faults. I remember when I was in physics back in the day, it was the same exact problem, but it was like a bench, a box, the box weighed a certain weight, it applied its own weight on the bench, and the bench was applying the same stress normally to the box. And then if you wanted to, which is equal to W, if you wanted to move the box like this, sorry, let me use a different color. You want to move the box like this, you're basically fighting friction that is trying to push the box backwards. And basically you had something like the driving force, and it was something F equals mu n. This is what you need to be applied, basically. It's the same thing here, actually. You have the rock, the pre-existing fault. You are trying to make it move using tau, but the rock is held. The fault is held. Excuse me. The fault plates are held together using sigma n. If you want to get slippage, if you do get slippage, it means that tau exceeds mu sigma n. So it's the same thing, basically. It's just that I'm not telling us in high school that the force that we applied to make the box move is shear. So the heavier the box, the harder it is to move it. Can you imagine this mouse here? I want to move it, apply shear, and make it move. What if it's heavier? If I take this big printer, I put it here, and I try to move it, I need a bigger force than what I need about this to make this mouse move. That's the idea. So the way I'm gonna do it now, when we say friction factor, it's just like any friction factor is dimensionless, blah, blah, blah. The easiest criterion to use mathematically is what we call the Moore-Coulomb criterion for shear failure or frictional failure, same thing is given. It relates tau with the normal stress. Now remember, when I say tau, it's an indirect stress. You are not applying tau. You are applying sigma 1 and sigma 3. All together, those two induce tau. Now, for a Moore-Coulomb criterion, this is the official definition. You have tau equals to tau naught, which is the cohesive strength, plus mu sigma n. A cohesive strength is the strength that holds the particles of the material together. Okay. For our purposes, it really depends. If you are using a small sample, you can assume that that sample is intact. So a small core, like the ones we use in the lab, we can assume that that core is intact. So there is cohesive strength, which you can quantify. If it's a big rock sample, like as big as this room or as big as this building, we assume that it has a lot of fractures in it. So we can neglect this tau under some circumstances. And it makes this equation even easier. But before that, let's see how it looks like, how the Moore-Coulomb criterion looks like in graphical. I have the failure envelope. It's basically that equation. I will use yellow, which normally signifies failure. Anything in this yellow region indicates failure. Okay, the equation for that line is tau equals tau naught plus sigma n times m. And then I have S1, the most compressive stress, and S3, the most least compressive stress. Now, if I take account of the pore pressure, what will happen is that my stresses decrease because pore pressure acts against them. So my circle from solid becomes dotted. So I'm moving to the left. Movement to the left means I'm getting closer to failure, okay? So pore pressure seems to be helping me fail. And we're going to talk about that maybe today or next lecture. But generally, if you cut that line, and we mentioned, and you cut into the yellow region of the shear failure envelope, you are in trouble. That's why you get failure. You don't want your circle to cut into that region. And of course, you can argue, okay, you have S1 and you have S3. What is the role of S2? Does it play a role? Under the Moore-Coulomb criterion, it does not. It doesn't matter what you have for S2. As long as it's between S1 and S3, it doesn't play a role in the failure. That is the simplicity of the Moore-Coulomb failure criterion, which is used quite a bit, I have to say, in fairly complex scientific research projects. They still use Moore-Coulomb is pretty powerful, and I use it a lot myself. Anybody who's doing induced seismicity work, which is when we do saltwater disposal and we increase the pore pressure too much and then we get failure, they use more Coulomb criteria for that, mostly. There are some others more complicated ones. Yeah, I have a student who did an internship in Dassault Systems, and he was doing my project. His name is Nassim, and he used to TA this class. Oh, he took this class the first time I was teaching it. I don't think he might have TA'd this class in 2024. I don't remember honestly, but he used a little bit more advanced failure criteria for shear. So the more circle should not cut into the failure envelope, otherwise we have issues. Now, for rocks with pre-existing faults, tau naught would be equal to 0, okay? With a big body of rock, you can assume that it has a lot of faults in it because they exist naturally. And that can help you, as it can help you simplify your equation to what I did earlier, tau equals mi sigma n. In that case, what will this do mathematically or graphically, sorry? It will do something like this. It's gonna move things like this. The line now becomes, all this becomes a failure envelope. Because the equation now is tau equals to 0 plus mu sigma n. Because this tau naught becomes 0 now. So the line moves down, the failure envelope becomes much bigger, and now you have failure with or without pore pressure, or like you get failure much, much easier than before. But when it comes to big rock bodies, this is a good assumption. Now, Byerly, he was for USGS. He died in 11 years ago, I remember, and I remember that because in his obituary, they put a picture of him when he was younger, and he was doing a lot of experiments in big rocks that you needed ladders to climb on, big blocks of rock for USGS, the United States Geological Survey. So you had these big blocks of rock, and he did a lot of experiments for them back in the 70s. And he wrote a book saying friction in faults, something like rock friction, something like that. And he said in the book, the friction factor of rock, pre-existing faults in rocks, is between 0.6 and 0.8, closer to 0.6 than 0.8, something like that, which helps us quantify this mu. Okay, we have evidence by somebody who did experiments over 40 years ago that said that for rocks, pre-existing faults have friction factors of 0.6 to 0.8, closer to 0.6 than 0.8, more or less. So we have an indication. He helped us simplify this even further, that equation. So basically, it reduced the equation to something like tau equals 0.6 sigma n, or 0.8, something between those. Oops. Now let me see. Yeah, I was gonna draw here a left space. That means I have to draw something more Coulomb, tau, sorry, more circle. This is tau equals 0.6 sigma n. Now, this is S1 or sigma 1, effective. And this is sigma 3. No failure. But if this is sigma 1 and this is sigma 3, certainly failure. Certainly failure. The stability of faults, or pre-existing faults, I should say, against shear slippage, frictional failure, is given by the condition I mentioned earlier. No, I didn't mention earlier. Now, this is basically the same equation. Okay, it looks weird, but this is basically how same thing. The conversion is done. If you have the book Reservoir Geomechanics in Zobak, you'll be able to see how this is done. Or if you have the book Petroleum-Related Rock Mechanics, you will see that. Same thing. It's the same equation. It's just derived in a, how do you say, transformed into different coordinate system that has sigma 1 and a sigma 3. Now the left side is basically sigma 1 over sigma 3. The right side is just one variable. Right-hand side is just one variable, mu. If mu is 0.6, this becomes 3.12. If this mu is 0.8, this becomes 4.33. So if I use 0.6 to 0.8, it means that I'm going to be between 3.12 and 4.33. Now, it doesn't mean that 0.55 is impossible. It doesn't mean that 0.85 is impossible. It doesn't mean that 1 is impossible. It's not impossible. It's, I was talking about Nasim and he just sent me a text. Yeah, I'm expecting the right-hand side to become something between 3.12 and 4.33 if I use 0.6 and 0.8. Just one variable. Only mu controls the right-hand side of the equation. On the left side of the equation is like sigma 1 divided by sigma 3. Now, the way they call it is like this. It can be confusing for students sometimes. If the left-hand side is, so if sigma 1 divided by sigma 3 is less than 3.12, assuming that mu is 0.6, it means that I'm stable. I don't have shear slippage. If it's bigger, if the left-hand side is bigger, and this equality is no longer valid, then I have failure. The way I converted this equation to, and I believe you spend a lot of time in geomechanics looking at this equation, I converted this to this is because in this form that we have here, I'm able to use it better when it comes to SV, SH max, SH min. I can put S1 what it is, I can put S3 what it is, and then I can put mu what I think it is, and then basically figure out if my value is good or not. So for instance, somebody tells me I have this stress state. They tell me SV is 10,000. They tell me SH max is 13,000. SH mean is 5,000. Pore pressure is 1,500. All PSI. And they also say assume that mu is 0.6. I would say, okay, do you think that this stress state exists? I would say, give me a second. Let me figure something out. I will come here, take this equation, and I will ask myself, what is S1? S1 is SH max. Is this S1? So I will do 13,000 minus pore pressure. What is pore pressure? Is 1,500 divided by what is S3? Is SH mean. 5,000 minus 1,500. I will calculate this value and see how does it relate to 3.12. Is it bigger or is it small? Sorry, smaller or bigger? And I will see. So 11, 13 minus 1.5. What is it? Something like that. And then it would be 3,500, something like that. So you do. Hey Siri, what is 115 divided by 35? And Siri will tell me that, thank you, Siri, it's 3.28, which means that this exceeds 3.12. And I will say, excuse me, sir, what you gave me is unlikely to be a stable stress state. Because if a fault exists under those stress state conditions, it will automatically fail in shear. There will be shear slippage, which is basically an earthquake. And they will say, oh, you must be very smart. What if you go to school? And I will say UND. But yeah, that's the idea here. It doesn't mean that any stress state given to you is stable and is possible to exist in the Earth subsurface. We talked about all this. So, yeah, that's the logic. And this is a very powerful equation. I use it a lot in research. I use it a lot when I was a student for my PhD, etc., etc. And I know other people who did the same. Oh, my keys got stuck. Anyway, that is the gist of it, I guess. Of course, there is several assumptions, and you can come up with a much more complex criteria. Doesn't mean that they will be as effective, but yeah, generally, when you talk to people with experience in this stuff, like Mark Zobak and the Jean-Eric Lusny, they do believe in this equation a lot, quite a bit. And they also believe in the assumption that that basically there is pre-existing faults all over the Earth subsurface that are oriented in every different location, which is what we call the critical faulting stress hypothesis. Actually, it was Barton and Zobak, 1995, that came up with this hypothesis, which basically said that for simplicity, we need to assume that if we look at the rock as a large scale, something like the Earth subsurface, we can assume that there is an infinite amount of faults. And because there is an infinite amount of faults, They can be oriented in any possible direction, and they can have any possible conditions. So say if I'm here and I say, okay, to have failure here, under those conditions that I'm looking at, I need to have a fault facing in this direction, being stressed at this value, having these properties, blah, blah, blah. I should assume that there is such a fault in this direction. That is the Barton and Zobak 1995 hypothesis, critical faulting stress hypothesis. It basically assumes that worst case scenario does exist everywhere due to the infinite, there is infinite possible orientations and conditions that a fault can exist in a rock, and it does exist basically. When I was talking to, when Jens-Erik Lundsny gave us a talk, fall of 2024, he actually suggested that this is a very good assumption. And yeah, I mean, I had a little bit of a reservation on it, but I think he's right in what he said. Like, it's much more, it makes more sense and makes the mathematics much, much easier. Because if this assumption wasn't right, I wouldn't be able to tell you, excuse me, sir, the values that you gave me are wrong because they create an unstable stress state. They will counteract my argument and say, sir, how do you say this equation assumes that there is a fault, critically oriented and stressed at that location? How realistic do you think that is? And I would say in large scale rocks, it's assumed to be quite realistic because of the Barton and Zobak 1995 critical faulting stress hypothesis. Okay. Any questions before I move on?
No, Professor, thank you.
Okay, sir. So now if we have time, we have 15 minutes. I think it's enough time. I will show you another way, which you probably already know, other than the more Coulomb diagram, to display this criteria that I mentioned earlier. And it's the stress polygons, which is a very powerful tool in geomechanics. The graphical display of the range of stress states that exist, that can exist by being stable in the Earth subsurface. I want you in one diagram to show me what is the range of stress states that I do think it will exist. So I don't have to do this little calculation I did earlier. I can look in a diagram and in a plot and give me the answer. And it's going to look something like this. And I want to say that was a big debate of people saying, who started this diagram, blah, blah, blah. I think it was on LinkedIn. People were complaining, oh, you know, it was so-and-so in this year. It was so-and-so in that year, blah, blah, blah. And I think Zobak said that it was him in something late 70s or early 80s or somewhere then, when he came up with the first version of the plot. Now, the version I'm using here is the one I like the most. Is from Nelson et al. 2005. Very, very, it's a lady. I think I don't know what happened. She was doing a PhD somewhere in Australia. And then I think she graduated and then started working for BP or something. I think she probably changed her last name or something. I don't know what, but it was very, very good paper. And the good thing about this plot is that it becomes dimensionless. So you are dealing with, units don't really matter. That's why I prefer using this version. And when I met Jens-Erik Lundsny last Christmas break, during the winter break, when I went to Golden, Colorado, he showed me some of his presentations. He's using the same version. And he used to be Zobac student, so they are familiar with this stuff. So this plot has SH max on the vertical axis and SH mean on the horizontal axis, both of them normalized by SV. So the units of both axes are none. They don't exist. They are dimensionless. So both axes are dimensionless. One has SH max normalized by SV. The other one has SH mean normalized by SV. The dotted diagonal, this little line here, is the line of horizontal isotropy. That is where SH max is equal to SH mean. Can SH mean be bigger than SH max? No. So anything below this diagonal cannot exist. It's impossible. So anything there is impossible, because that will imply that SH mean is bigger than SH max. So forget anything below the diagonal, only above the diagonal. And then we have those solid lines. These lines are what we call the frictional limits. Okay? It's that old equation I showed on the previous slide. The frictional limits at a given mu. In this case, the frictional limit at mu equals to 0.6, 0.6. I will show you how to draw those. But yeah, this is how they are. Now, anything above those limits, anything between the diagonal and the limit in this polygon inside is stable. It can exist in the Earth's subsurface. Anything outside is impossible. Anything here is stable, basically. Now, within the polygon, this little triangle here is normal faulting stress states, because SH max over SV is less than 1, and SH mean over SV is less than 1. So if I do my consideration, so here everything should be normal faulting, everything. So within the polygon, that portion, that little triangle at the bottom is normal fault. That triangle at the top, above SH max over SV equals to 1, but below SH mean over SV equals to 1, is strike slip faulting. And then the bigger triangle is above SH max over SV bigger than 1, SH mean over SV bigger than 1 is reverse faulting. And that is a little bit of I guess it's a surprising result for many of you, including myself when I was doing it for the first time. It was that if you look at the maps that people are building, like Jens-Erik Lundsny, most of the places on the Earth, we said they are normal faulting. But the range of stable stress states that are normal faulting is smaller than strike slip and reverse faulting, which is a little bit surprising. You have more reverse faulting stress states that can be stable in the Earth subsurface than you have strike slip faulting or normal fault. So that is something to remember because it's quite surprising, I would say, or counterintuitive a little bit. Now, we said the frictional limits depend on mu. They not only depend on mu, they depend on something else as well, and that is the pore pressure. Because remember, as we are gonna see, I don't want to show you this time because I need much more time to do it. Frictional limits are drawn using this equation. And there is pore pressure in this equation as well as mu. So it does matter. It does matter. Pore pressure matters. In fact, I will tell you qualitatively, if mu increases, the polygon becomes bigger. As mu increases, the polygon becomes bigger. Or as pore pressure decreases, the polygon becomes bigger. If pore pressure decreases, if pore pressure increases or mu decreases, we get a smaller one. So obviously, the smaller the polygon becomes, the range decreases. But still, I have more reverse faulting stress states that are possible to exist stably in the subsurface compared to strike slip and normal faulting, which is the surprising aspect that I mentioned earlier. So how are you gonna draw it? I don't know if you had this homework in geomechanics, but basically I make the students draw it and then save it for future reference. And that is the future reference that I was mentioning. But it's fairly easy to do so. But it can be tricky. You can get yourself confused very easily. But you can start from the easiest line first, which is the diagonal, the dotted diagonal. Let's just for simplicity, what I want to do, I want to call this X in inverted commas axis, and this Y in inverted commas axis. So X is SH. Oh, what am I doing? I did exactly the opposite. Oh, this is really stupid. Sorry, my bad. This is Y. This is X. Yeah, I can't believe I did this mistake. So X, when I refer to X, is SH min over SV. When I refer to Y, is SH max over SV. Okay. In my Excel spreadsheet, I will just say, okay, a series of X, please, from 0 to 3, a series of Y from 0 all the way to 3, a series to Y 0 to 3. That's all I need. And I plot it. So I get the dotted diagonal. Then I will proceed with the dotted line, the frictional limits. And remember, 3 lines. The easiest ones are this and this. The hardest one is this. So I will start from the easiest one. Let's start from normal faulting line, okay? I write this equation. I want this equation. What is wrong with this pen? This equation for normal faulting. So I will say something. S1 for normal faulting. What is S1 for normal faulting? The answer is SV minus PP. What is the S3 for normal faulting? The answer is SH mean. And then what will be the right-hand side? If I assume that mu is 0.6, it would be 3.12. So what I will do is that I will take the denominator, multiply 3.12. So I will get something like, let's do it straight, SH mean minus 3.12 pore pressure. Then, what if I, since I have something like, and let me erase now that I have SV minus PP equals 3.12 SH mean minus 3.12 PP. How about I divide by SV, everything by SV? What will happen is that SV over SV becomes 1. PP over SV is actually a constant. So I can say, okay, because the polygon is for a fixed pore pressure, I can say if it's hydrostatic, and I assume hydrostatic is 0.43, and then I divide by SV, which is 1, I can assume it's 1 psi per foot, it will be 0.433. So it becomes like a specific value. Let's just say 0.433 in this case. So does this, also a constant. But what is this? This is basically X, what we have here. So you can rearrange this equation. It's going to be something like 1 minus 0.43 equal 3.12 X minus 3.12 times 0.43. So I have an equation that is basically X equals something. X equals a value, and I believe it's going to be something like 0.62 for these numbers, something like that. And when you plot me in Excel a line that X is constant, what you are going to do is that you are going to go to Excel and go there and put X 0.62 all the way, 0.62 staying constant, and Y would be varying from, I don't know, 0 all the way to
0.62 all the way to 3 or 2.
Yeah. But I don't mind if you know, if you go to draw that, it's gonna be a line that looks like this. And then you can cut the part that doesn't make sense later on. So if we do it strictly speaking, you are gonna go from 0.62 until 1. But for this case, you can go out from 0 to 3 and then see which part you need to cut off. It's down to you. What you suggest is actually, it makes more sense if you go like from 0.62 to 1.
Yeah,
Basically.
because we said earlier, the shear minimum is equal to shear max. So 1 ratio 2.
Because it's normal faulting. Yeah, exactly. But this is one way to draw this line, the normal faulting line. Next time, we will go through the other two lines. I will show you how to draw this line, and then we are going to try to tackle this line, and then we should be all set with the polygon. The polygon is as powerful as the Mohr Coulomb diagram. Anything you can show on a Mohr Coulomb diagram, you can show it on a polygon. There is nothing in Mohr Coulomb, because why is the case? Because they are all based on the same equation. So anything you can show on one, you can show on the other. And yeah, I mean, it's just there are some things that the polygon is much more practical than others. And I think this is what I was trying to show. This is basically the equation that I solved. And yeah, I mean, you can give, if you give pore pressure in terms of SV, it's much easier. If you say something like pore pressure is 0.43 SV, automatically it's like, okay, the polygon I'm building is for pore pressure is equal to 0.43 SV, and SV mu equals to whatever, 0.6. Okay, thank you very much, guys. I will see you on Thursday. One thing is that office hours are tomorrow. Sometimes during office hours, they call me in the lab, I go to the restroom, stuff, whatever. If you come to the office hours and I'm not there, and you miss me by any chance, the Zoom might be on, but I might not see you. Send me an email or something. If you join the Zoom room and I haven't opened the Zoom room yet, I get an email so I can reach out to you and tell you that we can meet us, we can meet, etc. But if you go into the room and you cannot find me and I have left, please send me an email because I'm not going to be able to know that you have joined and left before when I come back. So thank you very much. Have a nice rest of your day.
Thank you, Professor. You too.
Thank you, Shamel. Thank you, Donald.
Thank you.